All right, well, with that, let's move on to our main presentation for this evening. I think many of you know Dean. You can see him in the picture here. He's going to give us a little talk about Arduinos. So, Dean, if you are ready, why don't you go ahead?
I'm ready. And so, everybody, I'm going to ask for your forbearance because I'm trying something new here. We're going to do a live demonstration. There are no PowerPoints, no death by PowerPoint tonight. But that means I've got to be efficient in changing from screen view to camera view and back and forth. And I practiced about 3 times today, but that doesn't mean it's all going to work. So we're gonna give it a shot. So first thing, what we're going to talk about tonight is the creation of a frequency generator. A frequency generator is a test device for your shack that allows you to generate a sine wave at a calibrated frequency and a calibrated amplitude so that you can use it to inject into your receiver or to test a VFO or to test an audio amplifier or any number of things. It's a very, very useful device. And the one we're going to build right in front of your eyes is based on just a couple of devices. So that's kind of the plan for tonight. Is we're gonna build, and what you see in front of you there on the display is the kind of black box with the 2 knobs and the switch. That's the signal generator. On the right of that is the breadboard version of it. That's what I'm going to build tonight. And then behind that is the oscilloscope, where you just see the trace that comes out of it. So that the box there is the finished box that you would end up with if you go through the same process that I did. So let me stop sharing, and you should now see my workbench. Everybody see that? So what you see here is the things that we're going to begin with. Okay, so let's start with breadboard. Okay, now I don't know if everybody knows what a breadboard is or not. Let's see, are we seeing me full screen? I want to make sure because I wasn't. So
I think it depends which view is on.
All right, so you want to be on speaker view because there's going to be a lot of detail here, so you want to be able to see it. But this is a prototyping breadboard. There's a couple of things that if you haven't seen one of these before that you need to know about it. The first is that along each of the edges is a power rail and a ground rail. Power rail and a ground rail. Those power rails and ground rails are not connected to each other, but you can jumper them together. And if you put in your positive voltage and your ground here, every pin on that rail will have the positive voltage, and every pin on that rail will have the ground voltage. We're going to use one rail as our input voltage, and the other rail is our control voltage for our devices. And I'll explain that a little bit more when we get to it. So that's first thing, the breadboard. And then each one of these, what will look like vertical stripes, or vertical rows of pins are connected to each other. So you can use each one of these, and it's just like a solder joint. This middle row is a division, so the things on the top and the bottom are not connected to each other. So that's a little bit how a breadboard works, and you can build all kinds of circuits on a breadboard. You can build little amplifiers and all kinds of things. Tonight we're going to build the signal generator on there, and we're gonna demonstrate how that works. Okay, you can see the components that make up the signal generator. This is an Arduino Nano. The Arduino Nano is a microcontroller. It's Atmega 328. I'm gonna look at my notes, make sure I got it. It's 8-bit, 16 megahertz. It has digital pins and analog pins and some memory, and it's essentially a little computer on a chip no bigger than your thumb. And that is the heart of the signal generator, because that's where the software that controls everything goes. It controls the display, it controls setting the frequency. That's the heart of the device. This is where this is the AD9850, an Analog Devices 9850 signal generator. It's a clock generator that is capable of producing a calibrated sine wave up to 62.5 megahertz. It can also produce a square wave up to that frequency. Although above about 20 megahertz, the square wave gets kind of squirrely and looks more like a mushroom than a square. So that device, excuse me, that device is the actual clock generator that generates the frequency. This here is the display. It's a 16 by 2 character liquid crystal display. It is controlled, connected by what's called an I2C interface. I2C is an old, dates back to the 90s. It's an onboard system bus interface that allows you to connect a lot of peripherals together. The great thing about it is it only takes 2 wires. It takes a clock and a data wire plus power and ground. And so it's very easy to hook up to your project. The other 2 pieces that are of interest, this is what's called a digital rotary encoder. And it allows you to turn the dial back and forth, determine left and right, and it also has a button that if you press, it's like a momentary button that can be used as a switch or a control for anything you want in your project. And then the last piece is 10K linear potentiometer, potentiometer, and what that does, it allows you to control the amplitude of the signal that comes in and out. So those are all the bits and pieces that go to. Of course, you got wires and jumpers that connected together. So now I'm going to switch back to the screen here. Share the screen again, and we'll talk a little bit about how you put it together and what the bits and pieces are. All right, so there's the Arduino Nano, and you can see it's got rows of pins on the left and right, 16 digital pins, 7 analog pins, and many of the pins do double duty. And a couple of the ones that we're particularly interested in for our build are the ones that run that I2C interface. So I2C SDA, that's the data interface. I2C SCL, that's the clock interface. That's how we're going to connect to the display. Others are just analog pin 7, analog pin 6, analog pin 5. You use those for whatever you want them for. You can put in your supply voltage up here at pin 30. That's where your input goes in. Or you can plug in a USB and you can take your power from the USB port, either way. But then, if the Arduino has an onboard power regulator, and it will put out a 5 volt or a 3.3 volt signal. So there's a 3.3 volt down here, and there's a 5 volt here at pin 27. We're going to use the 5 volts out in order to power the rest of the board. So that's the Arduino Nano. Fairly straightforward. When we get to the programming, I'll show you briefly how you turn those pins on and off, how you read those pins, and how they work. We're not going to spend a lot of time tonight on programming because this is not going to be a detailed programming lecture. I just want to give you a sense of what you can do with this kind of device. A microcontroller is really, really good for doing exactly what we're doing today, a small embedded system that's got some things that you want to control. If you've got high school kids who are in the robot clubs, they use these all the time. These are or variations of them. There's a ton of modules that you can plug in that are very easy to use. The AD9850, similarly, it's on the module. The chip there is the magic, and everything else is the stuff that gives you access to it. What we're particularly interested in is obviously the voltage in the ground, or how we're gonna power it. But we're gonna talk to a clock signal, a frequency update signal, a serial data signal, and a reset signal. And then we're gonna get our sine wave out off of this pin called sine wave out 2. So you get square wave 1, square wave 2, sine wave 1, sine wave 2. The difference between them is that the sine waves 1 and 2 are 180 degrees out of phase. The square waves are also 180 degrees out of phase. You can actually change the phase relationship between those with the software or with different hardware. We're not going to use any of these other pins. We're just going to use those to control it. So that's the, those are the two active devices. The other thing you're going to be interested in is, okay, well, how do I know how to put them together? And what do I do? And how do I figure out how they're going to go together? Well, you make some of those choices when you design your software. But then there's this nifty little program called fritzing, which allows you to draw just what you saw on the breadboard there. So you get to put your battery on there, you get to draw in where the wires go, what all the connections are. All of that is built into the fritzing software. So once you have your design, you can document that way, and then you can share this picture with people. And that way, if you're not comfortable looking at a traditional schematic, you have the other view. So if you're more comfortable looking at a schematic, here's the schematic. It's all generated actually from the same, I actually drew it using the kind of what you see is what you get editor here with the components, drag them on there, put the wires on, that sort of thing. And then the schematic got generated automatically. I had to clean up the traces and make them square lines and, you know, get them so that they weren't kind of crossing over everything. But it's pretty nice deal. And you can design all kinds of arbitrary things in there. So this is what we're going for. This is what we're going to build. Let's get started. All right, so first thing we're going to do is I cheated. I'm going to get rid of this one, and I'm going to bring in this one because it already has all of the plus and minus voltage wires plugged in, because I didn't want you to spend a whole lot of time watching me plug in little jumpers. And all the red and black wires are really is just the VCC and the ground wires. First thing I'm going to do is put my glasses on. You can't see that, but I need to see it so I can see what I'm doing here. And I'm going to plug in the Arduino Nano into the board. So this red wire here is +5, and this black wire here is ground. So I've got my power supply, which is just a 12-volt battery, coming in on the plus rail and the ground rail. And I'm connecting the ground to the Arduino, and I'm taking 5 volts out of the Arduino and putting it on this rail over here. So I have a 5-volt rail over there. First thing I want to do is make sure that this Arduino is actually working. So you program the Arduino via a USB interface back to your computer. So I'm going to plug it in now. There you go. It lit up. It's flashing lights. Okay, so it's alive, but what's it doing? Is it doing anything useful? Is it doing anything I need to do? What program is in it? I don't know. I just got it out of the box. It might be a project I used before. But what I'm going to do now is show you how you program the Arduino with a little test program that's going to show you how you then tell whether this thing is working. Now, the Arduino software, the Arduino Interactive Design Editor is this piece of software right here. And I'm going to load a program called Blink. And all Blink does is it makes an LED turn on and off in a 1-second increment. A couple of things you need to know about the Arduino IDE is it's going to connect to your Arduino Nano on a serial port. There it is, COM6, so that's fine. And then you have to make sure you tell it what board you're using. And you can see there's a whole bunch of different Arduino boards that are available. For our purposes, we're going to use the Arduino Nano tonight because that's what we've got. But there's a whole bunch of different devices. I've just been playing around with these things down here called Seeduinos, and they're even smaller. They're about the size of your thumbnail. So you've got a whole bunch of interesting devices. But for our purposes, the board we're going to program for is the Arduino Nano, and we're all set and ready to go. This program is very short. It does essentially one thing. It turns on, it says pin mode LED built-in output. It says, all right, I want the LED built-in output pin to be an output. And then it writes high, waits a second, and it writes low. And that writing high and write low puts out a voltage on that pin, and that turns on the LED and turns it off. To compile, which is what you do when you take a program and turn it from source code, which is what you're looking at, what you can read, into computer code, you just click on the checkbox here, And then down below it says compiling sketch. Sketch is the Arduino word for program. And once it's done compiling the sketch, it'll give you a thumbs up and say, okay, everything's good, or it'll give you 10,000 error messages, and you got to go figure out what's wrong. But since this is a demo and I practiced, it's perfect. Okay, so the sketch works. Okay, but that just means that the sketch has been programmed on my computer. It still hasn't been transferred to the Nano, to the microcontroller. In order to do that, I have to click on the arrow up here, and that's the upload arrow, and that will upload the program into the Nano. So before I do that, I'm going to switch back to the screen view, and what you'll see is when that sketch gets uploaded, you'll see the red LED start to blink kind of rapidly, and that'll show you that it's communicating with the PC. And then once it starts to run, you'll see a second LED that'll start blinking in 1 second increments. And there it goes. So 1 second increment. And that just tells me I've got a live Nano. It works. It can take a program. I've got it wired up right. I got the positive and negative set up right, and I'm all set to go. So step one, I did a test. I built something, and then I tested the thing that I built. All right. So what I need to do next is I want to hook up the display, and the next thing I want to do is see what the display does. So I'm going to unplug the USB port, and remember I said the display is only 4 wires. It's got a positive and a negative, and I've got my +5 rail here, and I've got my ground rail here. So that's really easy. And then I've got my serial clock and serial data lines, and those are the green and the yellow wires that come off of the back of the display. And I've got my cheat sheet here that I can use to look at them. I can say, all right, where do those things need to go? I'm not going to keep referring to this during the presentation because I've got it written down on a little notepad here. But you have this ready, and you say, all right, I know it's got to go where to where. All right. So I am going to go ahead and connect the negative and the +5. So that's just one into each rail. And then the yellow wire, which is the data wire, goes into the analog number 4 pin. And it's actually printed right there on the pin itself. It says A4. And if I get it plugged in right, that's A4. And then the green wire, which is the clock, that's going to go into pin 5. All right. So, fine business. Now I have hooked up my LCD. I'm going to power it on and see if the LCD comes on. Well, that's good news. The LCD has actually come on, but there's nothing on it because I haven't programmed it yet. There's no program. I'm still running the blink program, which only does one thing. It turns a LED on and off. All right, so what do I got to do next? I got to go back to the computer, and I'm going to upload a sketch to determine whether or not the LCD display is working properly. All right, so we're reconnected to the computer, and we'll go back to the screen sharing. And let me bring up the other sketch that I need, which is Hello World. All right, and share. Very good. So this is another sketch. This is a sketch that knows how to talk to an LCD display. This is a little more complicated than the one before, in that it has this statement up here that says include liquid crystal I2C.H. All that says is go get me the library, which is the term you use for a set of computer code that somebody else has written that you're going to take advantage of. I'm saying go get me the library that knows how to talk to the liquid crystal display. And then this line here says, I'm going to talk to the liquid crystal display at address 27, and it's a 16:2 display. Address 27 is related to that I2C device. It's a serial port. That's a serial bus, and each device on the bus has to have its own address. This one happens to be hex 27. An Arduino program has two sections to it. It has a setup that runs once, so it's called setup, and it runs once when you first power it on. And what it's going to do is it's going to call LCD init, which is initialize that LCD, and then there's some code in there to print stuff on the screen. And then, since all I'm really worried about is does the screen work, this program doesn't do anything else. There's a loop down here that just is going to run forever and do nothing. Okay, so I'm going to go ahead and compile and upload that to the Nano, and we will switch back to the display and see what happens. It should be uploading now, and it has reset. And let me go ahead and get a little more juice to it. And let's see, can we see that? Yeah, there we go. Hello, VWS, I'm Hal 9000. All right, so the LCD display is working. And that's really all we wanted to do with this stage, is make sure that the LCD was going to work. All right, so now we have tested the Nano, it's working. We've tested the LCD, it's working. We've uploaded sketches a couple of times. Our basic setup seems to be working. Next up, we've got to put in the clock generator and our controls and see where we get. So I'm going to go ahead and turn the power off and go ahead, I'll take the AD9850 clock generator, and I will plug that in and make sure I get it in the right place so that I have my pre-configured wires are connected. All right, so that's connected. I have the +5 rail voltage going to VCC. I have the ground going to ground. So if I turn it on right now, at a minimum, I should see the LED power light come on there. And I did. So the LED power light is on the device, so I know I've got my power connected properly. So I turn the power off again, and now I got to make my connections. And as I mentioned before, there's only 4 connections that we need to make. One is the clock, one is the frequency update, and those go right into this part of the board right here. The other is the data pin, and the last is the reset pin. And I made up a little, twisted wire cable here to make it a little easier for me to deal with. And I even wrote down where I wanted the color codes to go to make this quick. But the white is going to go into pin 10, 11. So 11, and the orange, which is the data pin, that goes to pin 10. And the yellow, which is the frequency update pin, that goes to pin 9. And the green, which is the clock, goes to pin 8. So that's the Nano side of the connection, which is the Nano is going to send commands out these 4 pins to the AD9850 signal generator. All right. So on the other side, the direction is clock and then frequency update. Yeah. So the clock goes first, and then the frequency update goes second. And I did these backwards when I tested earlier tonight, so I'm taking my time to make sure I get them right. All right. So 4 pins connected from the Nano to the AD9850 signal generator, and that takes care of the interface between the Nano and the signal generator. And so now what you have is you're almost done. Now you just got to hook up the controls and see what's going to happen. Now, I could test it right now by putting an oscilloscope on these output pins down here and seeing if there's a signal coming out. But rather than do that, I'm going to go ahead and hook up the controls and finish it up, and then we'll demonstrate how it's working and what it's doing. So the next thing that I'm going to do is I'm going to plug in the rotary encoder. And the rotary encoder has two sides to it. One side has 3 pins, and that's the A channel and the B channel and ground. And the A channel and the B channel and ground, or A channel and B channel, are how you determine left and right when you turn the encoder. And then on the other side are 2 pins, and those are just a switch. So when you push the button, those get connected together. And what will happen is one of those will go to ground, and one will go to a pin on the Arduino. And then when you push it, the Arduino will sense that the button's been pushed, and it can take whatever action you choose to take. All right, so let me make sure I get this in the right place. Again, it would be easier to do if I added the wires later, but I want to make sure I connect to the correct pins and the correct wires. All right, so I think I'm right there. So the black wire on this side is connecting ground to the encoder side of the control. The gray wire here is connecting ground to the button, to the switch. So now I need to connect the switch up to an Arduino pin, and I need to connect the A and the B channels up to an Arduino pin. So the switch, again, I go back to my cheat sheet, and I can say, okay, there's the switch that goes over here to A3, and then this one goes over here to D2, and this one goes, so the A and B go to D3 and D2. All right, so I got my plan. So the encoder switch is going to go from this side of the encoder to pin number A3 over here. So now my button should work. And then to get the left and right working, then I need to hook up the A channel of the encoder. So the A channel of the encoder is going to be a white jumper, and it's going to go to D2. So the A side goes over here to D2. And then the B side, just that third pin, goes over to D3. So now the encoder's hooked up, and if we turn it on now, we'll be able to see that whether or not it's going to work. Well, the interesting thing is we still have the hello world. Hello, VWS, I'm HAL 9000. So what does that mean? I got to go load the software for the actual encoder before we can test those things for the actual signal generator, so that we can actually test those things. So we'll plug this back in to the USB port, and we're going to go come back to the computer, and we'll upload our actual signal generator sketch. And let me share that so you can see what that looks like. There we are. So this is the sketch for the signal generator. This is much more complex than the previous ones that we looked at, but I'm going to walk you through it real briefly so you get a feel for what it takes to program something like this. Everything with a // in it is just a comment. It's just text to remind me of stuff that I needed to do. And so in here I said, if you want the data sheet for the AD9850, here's where you find it. If you want to know where to buy the digital signal generator, you can go to this link. If you want to know where to buy the library, if you want to know where the library of software that runs this thing came from, that's where you get it. So a couple of include DDS, that stands for Direct Digital Synthesizer, which is what the 9850 is. Liquid Crystal we saw before, and Rotary, that's a new one. That's the code that's gonna run our Rotary encoder. A few things to see here. I display my call sign on the startup. That's what this this is for, and I started up at 1 kilohertz, and I have the tuning increment. Each time you tune the knob, it's going to increase by 1 kilohertz. This is where you tell Arduino what those pins are. So remember I was talking about pin 8, 9, 10, and 11 being clock, frequency update, data, and reset. These lines of code tell the Arduino that's what I want those pins to be used for. And the encoder, encoder A and encoder B, 2 and 3, and the encoder button, A3, same. And then here is just a note, because we don't actually have to program the I2C pins because they're fixed. So for the I2C, which is the thing that drives the display, those are pins 4 and 5. And so that's just documented here. There's a little bit of magic code here that says, here's my direct digital synthesizer that I want to deal with from software. Here's the display, and here's the rotary encoder. And then there's some, software variables and constants for making things work. When we jump all the way down to the 2 routines, the setup routine, remember setup is called once when you power on the device. All it does is set things up so that things can run. And in this case, it means set up the interrupt routine. And I won't go into what that is, but it's a way that you can read the digital encoder. Set up the pins, which means tell the Arduino what pins are being used for what and how they're being used. Set up the synthesizer, the DDS, and set up the display. So each one of those is a function that does something. So set up display, initializes the display, turns off the backlight, puts my call sign on there, and so on. And each one of those little routines does some setup to get things going. After the setup routine is done, the Arduino environment transitions to this thing called loop down below. And loop will run everything in that loop in series over and over and over again infinitely. It just runs forever. There's no on-off switch or anything. It just runs and runs and runs. And all the loop does, because all this thing is a frequency generator, is it checks the encoder to see if you've turned it left or right, and it checks the increment, which is the button, to see if you want to change the tuning increment, say from 1 kilohertz to 1 megahertz, so that when you tune one click, it changes the tuning by 1 megahertz. So I've plugged it back into the Nano. I have my sketch all loaded up here. I have my libraries loaded. I'm going to go ahead and hit the button. That's going to compile the sketch and upload it. While that is happening, I can show you that there's a couple other files in this project. This is the one that runs the rotary encoder. I didn't write this. I borrowed it from somebody else in the world of open source software. Almost everything is stolen from somebody else. Even the core routines to run all of these pieces, I didn't write any of those. I just wrote the pieces that kind of cobble them together to make the thing actually work. So now the frequency generated code has been uploaded to the sketch. So we will switch back and we'll take a look and see what we got. All right, so it is coming up. It says KK4 DAS 809850 signal generator, and there is the display. It's showing. Let me see if I can make it so you can see it a little better. Getting some reflections. Let me try this again here. All right, so it's showing that the frequency is set to 1 kilohertz, and the frequency update is set to 1 kilohertz, which means every time I turn the dial, it should go from 1 to 2 to 3 to 4. Now that's good, because that says that the encoder is working properly, that I can tell clockwise and counterclockwise. And then the button controls the frequency change increment. So when I hit the button, it's going to go from 1 kilohertz to 10 to 100 to 1 megahertz. All right, so the controls are all working. But that does not tell me that the frequency generator is actually generating a frequency. All it tells me is that the controls are working and the display is working. In order to see if the a frequency generator is actually generating a signal, I need to hook up the output. And the way we're wired up is the output signal, sine wave, comes out on this gray wire here over to here, and that's where we're going to put our 10K linear potentiometer, because that's going to be our attenuator that's going to allow us to turn the amplitude up and down. And if you don't know how a pot works, real simply, you bring, in this particular configuration, you bring the signal in to one pin. The middle pin is is connected to the wiper. It's the thing that connects the resistor, the variable resistor across the pins. That's called the wiper. And so the middle pin is your output. And then the right-hand pin here is going to be connected to ground. And so what that will do is it'll create essentially a variable attenuator for the signal generator. And we just plug that right in there. And I already have all the wires hooked up. And we are at 1 kilohertz. And so now is the test to see whether or not we have a frequency generator generating a frequency. And so the white pin here is the output, and the black pin is the ground. And take a look at the oscilloscope. So bear with me here while I adjust the camera. All right, so there's the 1 kilohertz sine wave on the oscilloscope. And now I'll go ahead and turn the frequency up. I'll go to 2, let's say it's 100. Let me get back into the right scale here. So 2, 3, 4, 5, 6, 7, 8, 9, so on. And so you can see the frequency is changing. The attenuator can reduce the size of the signal and increase the size of the signal, so it's working. Let's go up to, we're at 13 kilohertz right now. Let's go up to 7.213 and see what it looks like at something like a ham frequency. So the 1 kilohertz is more like an audio frequency. So now I'll jump it up to 7.213. And there we are with a 7 megahertz signal. So you could use that to test your 40 meter transceiver. You could use it to test a filter if you wanted to plug a known frequency in and see what the bandwidth of your filter is. If you want to use it to check again a filter bandwidth, or to stimulate the exciter with a known frequency, so you can see how your receiver is working. If you need to calibrate a VFO, all of these things are things you can do with a frequency generator of known signal. So I wasn't sure I was going to be able to get through everything, and I rushed through a lot of things. So I think what I'd like to do now is stop and take questions, because we got through the build, and you see that it is possible to build this thing in a relatively short period of time with some preparation. I guess before I do that, let me show you a couple of things on the screen here. I want to show you kind of how I finished it up. I bought a plastic case from Marlon P. Jones, some circuit boards that I soldered the Nano to and the 809850. Got some connectors to put on the outside. I got an SNA connector so that I could actually connect it up to my scope and make it easier to deal with, and got it set up in a nice box. So there's it, kind of getting ready to put it all together, and kind of there's what it looks like in action. So with that, let me stop and take any questions. I don't know if there are questions in the chat, or if anybody had questions here.
I have not a question, but a comment. I highly recommend this kind of encoders. They're slightly more expensive without the button, but they have a nice crank.
Oh yeah, so you can, there's all kinds of things you can use. This entire, I didn't mention the prices. So an Arduino Nano costs about $4. The DDS board itself costs about $12. The LCD displays are, I bought 2 of them for $8, and a couple of bucks each for the, not even a couple of bucks each for the encoder and the, so this is very much on the cheap. There's a whole bunch of different devices and things you can use to control it on top of that. But that's just kind of the basics for a pretty simple, easy to make kit.
Yeah, so this one costs $20 instead of $2, but it's really worth it.
Right, so that costs more than the rest of my project. So
where can you get that encoder?
I think, I don't remember. I think I bought it either on Banggood or AliExpress, but you can also find them on Amazon, but they still ship from China. Just search for CNC hand crank.
So I'm looking at the, I'm sorry, yes, yeah. So I'm looking at the questions in the chat. What language are you programming? Is this specific to the Arduino? So no, it is not. It is the C language or C++ language. And the Arduino has its kind of variant of it, but it's based on, if you're familiar with programming, it's based on the GCC compiler, the GNU C compiler, which is the core compiler behind the Linux operating system and most of the open source software that you see for Linux. So it's all written in C. And then there's an Arduino IDE specific implementation of that particular interface.
Hey, Dean, did you look at all into adding modulation capability to your signal generator?
I have not, but that is another thing that I would like to be able to do, because if you could add modulation, then you could generate an AM signal and so on. So that would be a good extension to do. The great thing about these projects, though, is as you can see, they're so simple that it's fairly straightforward to do all kinds of different things at this point. And there are more pins available on the Arduino to do just about anything you'd like to do. I use the same basic configuration of the Arduino with another clock generator as the VFO and control for my my single sideband transceiver.
How about a frequency source? Do you have any experience with using an external frequency source such as a GPS DO instead of the clock that's on board?
I do not. However, there are GPS modules that will interface to the Arduino. So I know that, and I know that others have done and use that.
Just for your information, that particular oscillator he has is a clock of 125 megahertz.
Right, the clock's 125 megahertz, but you can only, because the way it's configured, you can get a frequency out of 62.5 megahertz.
Hey, Dean, do you suppose if you were to use that as a high frequency oscillator in a, in a receiver, could you program an offset into the display so it would display the frequency that you were actually receiving? I'm wondering if that would be real difficult or thought about.
It would take 5 seconds. That's how difficult it would be. So once you're in software, those decisions, what you display for the frequency, are trivial. They're really trivial. I mean, it really is just a couple lines of code to program in the offset. So for my single sideband receiver, I have to keep track of the fact that I have an LO that I'm controlling and a BFO that I'm controlling, and then I have the frequency that I'm displaying, and I have to take care of those calculations in the software. But there is no complicated hardware to generate these at all. There's no tuned oscillators and crystals or anything like that. It's all done by making a few adjustments in the software. So very straightforward to do exactly that. And in fact, this AD9850 is used in a bunch of homebrew rigs to do exactly that.
What's the upper frequency limit?
62.5 megahertz. As you get above about 40, the quality of the sine wave tends to drop off a little. Let me see. Let me pump it up a little bit and see. That's at 7. And you can see the what's happening is as you get a higher frequency, you don't have as much amplitude. So the strength drops up.
It's the filter you have to stick on the output of that thing to make a sine wave. It tends to roll off. It turns out the DDSs, if you're really careful and sneaky, there's like a secondary, like an alias mode that's like a harmonic, and you can actually go like double the frequency.
You can, and this module actually has the filter on it, so that's what's keeping everything nice and clean there. So that's at 20 megahertz right there. Let me go up to. All right, so that's at 40 megahertz, and you see it's starting to get a little squirrely, and not as clean. It actually does better in the case with all the loose wires and the noise, because now you're starting to pick up noise just from the floppy leads from the setup here. But that's at 40 megahertz, 45, and then it's kind of a mess now. That's at 58. So anyway, it's probably really useful up to about 40 megahertz, and then it starts to kind of drop off. And you might be able to improve it, but I haven't spent any time on that because I'm mostly interested in HF.
Yeah, Dean, I actually have designed, I have an oscillator, different one based on a 9851. And I've done the same thing. I've actually done it where I would have offsets. I'd have half frequencies or offsets. In fact, I have it set up where it would only allow you to tune in the ham bands.
Right. So all of that is very easy to do once you master the basics of the software. Now, if you've never done software, there's going to be a bit of a learning curve, but it's considerably less than it would have been just a few years ago because of the advent of these tools like the Arduino IDE, the Interactive Development Environment. So much of it is done for you in libraries. So for instance, to write the code to control the AD9850 is complicated. There's a lot of complex signaling that has to go on to actually get that chip to generate the frequency the way you want it to in the phase that you want it to. You don't have to think about any of that. All you do is say, okay, library, I want 7.2 megahertz, and it does the rest. You don't have to worry about the signal lines and all that. There's all those lines I hooked up. Some software in a library that somebody else wrote is providing the actual controls for those. I just need to know how to interface to their library, which interfaces to the actual device.
Where can we get the code?
I will upload to GitHub and send a link to everybody, the link to my entire sketch. And then in the sketch itself is the code for the DDS library and where you can download the original. I can obviously send a copy of it, but you're better off getting the original in case he's made changes or updates to it. But that's documented. That is documented in the sketch and right here. m0xpd.blogspot.com, DDS libraries. But in any case, I'll make sure that I include that in the kind of follow-up right after this. And obviously, if you want the code, Kevin, just send me a note and I'll just package it up and send you the whole thing.
Thank you. I do appreciate that because as I say, I want to take the DDSs I've designed were written in PicAxe, which is kind of a reduced instruction set basic, but it's very hard to program. And it would be really nice if I could come up with a couple of little C codes and just put it in the same program as A or now.
Yeah, so what Kevin's talking about is PicAxe is another microcontroller architecture that predates the Arduinos. And when the Arduinos came on the scene, they were really meant for like students to make it easy for them to program microcontrollers like the robotics crowd and all that sort of thing. But they have really caught on in the maker community, and they've really caught on in the ham radio maker community that works with these small devices. It's actually what's made it possible for somebody like me, who is not an electrical engineer and does not have an electronics background of any significance, to build a single sideband transceiver, because the chip that I use, the SI5351, generates the frequencies. And the most complicated part of a single sideband transceiver is getting those oscillators at the right frequency and getting them stable. And here, you tune it, you program it in, and you get a stable signal out. So, if people are interested in this sort of thing, these are the kind of things that I hope we'll do with our maker community as we roll up now. I think you may know that I have officially retired from my full-time job. I have a little more time now, and I'm going to try and get. We've got our. You can now go on the VWS website and sign up for the maker mailing list. That works again. I'm now the administrator of it. So if people will start signing up for that are interested in maker activities, I will start sending out updates, and we'll get a few things going.
Excellent.
Super, Andrew. So let me stop sharing, and thanks everybody. I hope that was enjoyable and interesting, and not too geeky.
Anybody else have any questions for Dean? Or if not, I think at this point we're pretty much done with our main meeting, the official meeting. So from this point, if you would like to, feel free to stick around, but the official meeting is, official VWS meeting is actually over. So, but please feel free to stick around and socialize with anyone who's still here. I know I'm going to stick around a little bit, as I usually do. And I know you're seeing this orange thing. I'm going to reveal myself once again, but I will say once again, thank you, Dean. That was really cool.
Oh, you're welcome.
Thank you.
Yeah, really well done.